This video is just going to quickly go over some of the highlights from the different postulates that make up our quantum mechanical theory. The first postulate has to do with the wave function psi. So this is essentially the quantity that contains all of the information that you need to know about your system. Okay, it's position, time evolution, basically any information that has to do with your system is contained in your wave function. Now the key here is that there are only certain functions that will make a suitable wave function, and there are certain conditions that have to be satisfied for our wave function to be valid. And these are the four conditions for having a suitable wave function. You'll get some practice on that in the homework, but we need a single valued function. The wave function and its derivative must be continuous. It must be finite, and it must be quadratically integrable or square integrable. So essentially that means that if you take the integral of the square of your function, so psi times psi, you end up with a finite value. Okay, so and we'll see that this idea of a normalized wave function is a consequence of that fourth condition. Okay, and we'll talk about that more as we go on throughout the course. Okay, so second postulate states that to every observable in classical mechanics there corresponds a linear Hermitian operator in quantum mechanics. Now the first thing I'll mention is that this idea of a linear Hermitian operator, we're going to talk about those qualities a little bit down the road. Hermitian operators, that's one of our theorems of quantum mechanics. We're going to hold off on talking about those details for right now, but for now just know that there is a quantum mechanical operator for any physical property that you would be interested in measuring. Okay, so things like position, momentum, kinetic energy, okay, and these operators are indicated with little hats on top of the notation. So if we have an operator A, whatever that operator might do, we indicate that with a little hat on top. Now Macquarie has a table of all the different operators that will interact with a lot this semester. Okay, so you can look and see what the position and momentum and kinetic energy and angular momentum operators look like. But essentially an operator is just a mathematical instruction for what you're going to do to a function. So an operator by itself doesn't really have any meaning, but at some point we will be having these operators act on our wave function, and that will give us a useful result. Okay, so third postulate is where we put our operators into action. So here is where we encounter what we call eigenvalue equations and eigenfunctions and eigenvalues. Okay, so this form of equation right here is what we call an eigenvalue equation. So you may have seen this type of equation before in a math class. We will use this a lot to calculate different quantities. So this is how we essentially get calculations for the different observable properties that we're interested in. So the basic idea of an eigenvalue equation is that we have an operator, operator A, just a general operator. It's going to act on our wave function, in this case psi, and then that's going to spit out our same function back. So we get our psi back, we get our wave function back, times a constant represented by A. Okay, that is the premise of an eigenvalue equation. It is not the same idea as an algebraic equation. You're not just multiplying these things together. Okay, it's your operator acting on your wave function, spitting out your wave function back at you. So you'll get the same wave function back that you started with over here, but it's going to be multiplied by some constant. Okay, and if you don't have that situation, then you don't have an eigenvalue equation, or you don't have a wave function that is a eigenfunction of your operator. Now, the beauty of the eigenvalue equation is that when we solve the eigenvalue equation for a particular operator, the only measurable quantities that we'll obtain are the eigenvalues that result from solving our eigenvalue equation. Okay, so we're only ever going to measure these A's, these constants. Okay, these are our eigenvalues. So here A is what we call the eigenvalue, or characteristic value if you have taken German. So we'll see down the road that for a particle in a box, the only possible values are these values here, corresponding to the different n values, the different states that we could have. There are no other values possible to measure. You will only ever measure an eigenvalue. That is the solution to your eigenvalue equation. Okay, so again, to go a little further, if you know what state you're in, if you know that you're in, let's say for a particle in a box, and you're in state 3, so you have psi 3 as your wave function, the only possible energy that you're going to measure is the energy that corresponds to state 3. So in this case, that would be, this is n equals 1, n equals 2, and n equals 3. So the only thing that we'll measure, if we know that we're in state 3, is that eigenvalue that corresponds to psi 3. Okay? There's no ifs, ands, or buts. That's the only thing that you will measure for that particular state, no matter how many times you measure it. Okay, so just for argument's sake, let's say that instead of being in an actual eigenstate of your system, okay, so instead of being in state 3, let's say that we're in a state, or our particle's in a state described by this equation here. Now, first question to ask yourself is this an acceptable function? Right, so remember, we still have to satisfy our first postulate. Is our wave function an acceptable wave function? Okay, so it's plotted here, and visually it's pretty easy to say that yes, this is an acceptable wave function. It's single-valued, continuous, finite, square integrable, so there's nothing wrong with this particular function in terms of being an acceptable wave function. Okay, there's nothing that says that our particle has to be in a state that's an eigenfunction of the Hamiltonian. Okay, it does make life easy, but it doesn't necessarily have to be the case. But the question we ask ourselves is, okay, so I have this particle in a state that's not necessarily a state that is an eigenfunction, okay, of my system. So what do we get when we do measurements? Okay, well, once again, remember back to postulate 3. Okay, so even if your particle is not in an eigenfunction or an eigenstate of your system, okay, you're still only going to measure eigenvalues, okay, that agree with postulate 3. So we're still only going to measure those eigenvalues that are associated with our particle in a box system. Okay, you're not going to be able to predict which one you're going to get. You could get any one of those, and you'll get some distribution of them. And we'll talk a little bit down the line about how we can get a measure of the spread in our measurement values. Okay, but when you do a measurement on a particle in a box system, you will only ever obtain eigenvalues of your particle in a box system. Okay, so even if your particle's in a state that's not an eigenstate of your system, you're still only going to measure, you're only ever going to measure the eigenvalues that correspond to your system. Okay, and our fourth postulate has to do with calculating average values. Okay, so we're going to use this postulate a lot. We've seen this a little bit previously in thermodynamics. Okay, but we're going to use this approach a lot this semester to calculate the average value of different quantities. So average position, average momentum, average energy. Okay, this is the tool that we're going to use to calculate average values. Now, we'll practice this a lot in class and in some homework assignments, okay, how to actually execute this calculation. But one thing that is important to note is that the average value that you calculate is not necessarily going to be one of the eigenvalues. Okay, so don't get caught up in applying postulate 3 to your average values. Okay, so postulate 3 only applies to your eigenvalue equation. Okay, when you're calculating an average value, you can get any value. It does not necessarily have to be one of your eigenvalues for your system. Okay, and our final postulate that we're going to talk about right now is the fifth postulate, which states that the wave function evolves in time according to the time-dependent Schrödinger equation. Remember, the Schrödinger equation is our central equation in quantum mechanics. We're going to become good friends with that over the next few weeks. Okay, H is what we call a Hamiltonian operator. It represents the operator for the total energy of our system, and we know that our total energy is always the sum of the kinetic energy and potential energy. Okay, so this total energy operator will be valid for any system. This is always going to be the case for our total energy. Okay, one thing to note is that our kinetic energy never depends on time. Okay, and actually, since 99% of chemistry is time independent for our potential energy operator, most of the semester we will concern ourselves primarily with what we call the time independent Schrödinger equation. Okay, so that simplifies things a lot for us. And when you get to grad school, you'll spend a lot more time looking at the time-dependent version of the equation. But we'll simplify things as we start out and just focus on time-independent systems. Okay, so that's it for our quick overview of the postulates of quantum mechanics. We will put these into use in class and on some homework assignments. And I'll also make a few more videos that go explicitly into the applications of eigenvalue equations and calculating average values and things like that. But hopefully this just gives you a little bit of a sense of kind of where we're going. All right, thanks.